limitations of pH scale. What do you think? pH scale 0 to 14 is always true, always correct, or do we have anything more to that? Yes, sometimes you will get pH 0, pH less than 0. As in, if I take, let's suppose, if I take normality or molarity equals to 10, normality or molarity equals to 10. That means if you take pH, you will find negative log of 10 comes out to be -1. So, what do you say? Your formula for pH is wrong, is it? We are very smart people. So, what we do is we never take concentrations as high as 10 molar or 10 normal. What we have been taking, we take concentrations so that we take concentrations which have 10 to the power minus 1, 10 to the power minus 2, 10 to the power minus 3. So, we always get positive number, right? We are very smart people. We never get, you will never get, rarely get in any question negative pH, right? Why is that so? That is because we never deal with higher concentration solutions. We are dealing with concentrations like 10 to power minus 1, 10 to power minus 2, 10 to power minus 3, something like that. So, because of that, we never get negative pH, but yes, you can get negative pH, what I told you just now, right? So, this is some flaw, or we can say limitations, which was not explained in pH scale. And another thing is pH. pH it represents power of hydrogen or H plus concentration, but how it is related with H plus? If pH goes down, H plus concentration goes up. That means lower the pH, higher will be H plus concentration and higher will be acidic character. Higher will be acidic character. So, pH doesn't tell you directly how acidic a solution is. What should have been the case? Higher the pH, higher the acidic character, but it is inverse of it. Lesser the pH, more is acidic character. So, it doesn't give a good idea about acidic character, but we are students of chemistry, so we can make out that less pH means more acidic, more pH means less acidic. Alright, so that is some limitations. And if you take a solution of pH, let's say 1, and you take another solution of pH 3, what do you think? What is the relation? What will be the H plus concentration in this? So, H plus concentration is written as 10 to the power minus of pH. So, here the H plus concentration is 10 to the power minus 1, and here H plus concentration will be 10 to the power minus of pH, that is 10 to the power minus 3. So, what do you think? 10 to the power minus 3 and 10 to the power minus 3 and 10 to the power minus 1. What is the ratio? 10 to the power minus 1 and 10 to the power minus 3. What is you will get? You will get 10 to the power 2. That means the H plus concentration ratio of first solution to H plus concentration ratio of second solution is 10 to the power 2. That means H plus concentration of first solution is 100 times H plus concentration of second solution. Whereas in pH, what you get an idea that there is a difference of acidic character 2 units, right? But actually, the difference in H plus concentration is 100 times. H plus concentration in first solution is 100 times H plus concentration in second solution. Whereas pH 1 to pH 3 you go, it appears as if there is a difference of 2 units in acidic character. So, this is something which doesn't give a good idea about acidic character, but that is how it is. That is why we are saying this is a limitation of pH scale, right? Now, we have another important concept called common ion effect. So, what is common ion effect? Common ion effect, I will explain it to you. What it is, if you have a weak electrolyte, let's say carboxylic acid, it ionizes as acetate ion and H plus. Now, if you take any electrolyte, any strong electrolyte which can provide acetate ion or H plus, then there will be common ion effect. For example, If I take HCl in this same solution, I apply this, what will happen is it will give Cl minus and it will give H plus. So what happens is it is a strong electrolyte. It is a strong acid, so strong electrolyte, and this is a weak electrolyte. So equilibrium is always written for a weak electrolyte. So what happens? This H plus in the solution, this is in the same container. So what happens is this H plus concentration adds up to this. So overall concentration in H plus here increases. So reaction keeps moving backwards. So if reaction keeps moving backwards due to common ion provided by a strong electrolyte HCl, this H plus was there, and this electrolyte, this is a strong electrolyte, it also produced H plus. So there is a common ion present in the solution. So this H plus will increase this H plus concentration and reaction falls backward. So ionization of acetic acid decreases due to presence of common ion. This is known as common ion effect. So higher the concentration of common ion, less will be the ionization of weak electrolyte. As in this case, acetic acid will be less ionized if HCl is present because it provides common ion H plus. So common ion effect is less dissociation of a weak electrolyte in the presence of a strong electrolyte having common ion. Buffer solutions. So have you heard of them? Have you came across a buffer solution? No, you don't know, right? I'll tell you. Have you heard of blood? A human body has blood. Whenever you get injured, it comes out. So blood is an example of buffer solution, right? And the pH of blood is 7.4. It is slightly alkaline or basic in nature, our blood. So blood is an example of buffer solution, and it is a buffer solution of bicarbonate and carbonic acid combination. What happens over here is we have taken few examples of acidic and basic buffer. So let's begin this topic with understanding what a buffer solution is. Buffer solution is a solution which can resist a small change in concentration of H plus and a small change in concentration of OH minus ions. That means pH does not changes much in the when a small acid is added or a small amount of base is added. Such solution which can maintain its pH over a range of pH values, it is known as buffer solution. So how you will figure out whether this is a buffer or not? I will explain it to you. In acidic buffer, we take weak acid and its salt with a strong base. What? Weak acid and salt of that weak acid with strong base. Example, we have taken a weak acid, acetic acid, and its salt with NaOH. So acetic acid and NaOH react to give sodium acetate. So weak acid, acetic acid, and salt of acetic acid with strong base NaOH, that is sodium acetate. So this is a basic, this is a acidic buffer. Same way, if you take weak base and take its solution with salt of weak base and strong acid. So either you take weak acid plus salt of weak acid with strong base or this is acidic buffer and basic buffer. What you get is basic buffer. This is acidic buffer and acidic basic buffer will be like this, that we will take weak base plus salt of weak base with strong acid, right? So that is what we have taken few examples: weak acid, acetic acid and sodium acetate, weak acid, boric acid and borate, phosphoric acid, sodium phosphate, formic acid and sodium formate. These are some examples of acidic buffer. Similarly, we have basic buffer, weak base ammonia and ammonium chloride, ammonium hydroxide with ammonium chloride, NH4OH with ammonium nitrate, NH4OH with ammonium sulfate. So these are examples of basic buffer. Now we are going to understand buffer action, how buffer works, that on addition of small acid or small base, pH does not change. Let's see. Buffer action. If I take acidic buffer, let's say you have sodium acid, acetic acid, acetate ion plus H plus, and you take sodium acetate. So what happens? This gives acetate ion plus Na plus. Now, if you add a small amount of acid, then you are adding H plus. So what will happen is, if H plus is added, that acidic strength increases. What happens is, this acetate ion captures this H plus and forms H plus and acetate plus H plus gives acetic acid, right? So what happens is that this extra H plus is converted into weak acid, acetic acid. So H plus doesn't change pH much. Similarly, if I add base, that means we are adding OH minus. What will happen when OH minus comes? If nothing happens, OH minus will increase its basic nature. So this H plus captures this OH minus and converts coming OH minus into water, right? So this OH minus is used up, so it does not affect the pH of the buffer. In this way, basic buffer will also function and the pH of the buffer will be maintained as such. No change will happen on addition of a small amount of acid or a small amount of base. Now, for calculation of pH of buffer, we have Henderson-Hasselbalch equation, which have been given out here. pH of an acidic buffer equals to pH equals to pKa plus log salt concentration upon acid concentration. Similarly, for basic buffer, there is an indirect method. First, you will calculate pOH equals to pKb plus log salt concentration upon base concentration. Then you will subtract pOH from 14 to get pH, right? So these equations are known as Henderson-Hasselbalch equation for the calculation of pH of acidic buffer and pH of basic buffer. That's it.